Raj, I have your first slide, so just let me know when you want to advance.
Yeah, sounds good. Thank you, Jenny. So yeah, so as Jenny mentioned, so me and Robert will talk about the in silico usage of in silico algorithms for variant interpretation largely. So so this slide essentially shows the ACMG guidelines, and in orange or green are the ones where in silico a computational tool has at least some role to play in generating the evidence. And as you can see, it's pretty much most of it. And there are several different types of in silico tools which you could use. And in the interest of time, I won't be able to go through all of them, but I have made a list, which I'll show in the next slide, that covers the tools and the sources of the tools that are available in, oh, Jenny, can you go back to the previous slide? Sorry. That are available, and you can try it out. And those are the evidence tags that are shown in orange. And I will mostly be talking about in silico tools for missense variants and splicing variants, and which are indicated here in green. So if you go to the next slide. So essentially, this is the kind of a snapshot of a larger table, which I couldn't fit in here, that I have, and I will be happy to send it around, and which basically has the evidence code, the corresponding type of evidence, and there are several tools and the links to them, which would be helpful for generating helping making an inference about the ACMG evidence code. For example, for mutation hotspot, if you have a collection of mutants, you could use just, for example, Bioportal to generate to look at whether the pathogenic variants are arranged in some hotspot in some protein domain or not. And there are several other examples and links which I don't have time to go through. But what I will be, and Robert, I will be talking mostly about the missense variants, and Robert will be talking about the splicing variants, and also if a structure for a protein is available, how to interpret it and the caveats of it later. And as I said, I'm happy to send out the larger table, which has a compilation of the in silico tools and the evidence types, and also this omictools.com. This link has basically a curated set of functional prediction algorithms that are available. So Jenny, if you go to the next slide. So as I mentioned, I was talking about the missense variants, and Robert will talk about the splicing and the variants impacting the 3D structure. And when I talk about the missense variants, I will just, the outline would be like, I'll show you what are the caveats, what are the algorithms that are available, and there will be some suggested solutions, or at least one needs to be mindful of these caveats before making an inference. So again, if you go to the next slide. So there is a guideline, as you may all know, from the ACMG Richards et al. Guideline, which says that if all in silico programs tested agree on the prediction, then this evidence can be counted as supporting. So if in silico predictions disagree, then you do not count that. Now the thing is that, first thing is that this is a really broad definition, broad guidelines, so it could be interpreted differently by different person, given that, or different labs, given that there are in silico algorithms that are coming out pretty much every month in every month. So the question is, how do you choose amongst themselves? And there is also no specification of how to really use this large choice, which ones to use from this large group of algorithms. So for example, again, if you click on it, for example, this is a subtle thing that for example, people use Polyphen, but in this guideline there's no it says nothing about which type of Polyphen to use. There are two types of Polyphens, HVAR and HDIV. Those have different training sets. So HDIV, for example, includes a majority of the Mendelian mutations in the training set, so it's probably not best for the kind of mutations that variants that you'll be curating for the ACMG. AM guidelines, using the ACMG AM guidelines, and it's more useful, as they say in their, user manual, is for GWAS studies and natural selection. HBAR, on the other hand, is more suitable. So you would like to use HBAR as opposed to HDIV when you're using Polyphen, when you're using the ACMG AM guidelines. But this is not really clear from the guidelines. I mean, this is just one example, and I'll go through at least four caveats that you may run into if you are using literally this guideline. So if you go to the next slide, Jenny. So what, in this case, to show you the caveat, what I've done is like I've taken some 15,000 missense benign and pathogenic variants from ClinVar and annotated them with 18 in silico algorithms using DBNSFP 3.2 and then tested the applicability of the ACMG AM rule. So, Jenny, if you go to the next slide. So this figure shows that each row is a variant, and this pathogenic and benign, these panels means that ClinVar is designated pathogenic and in ClinVar is designated benign. And each column is a prediction by an algorithm, which is shown here on the x-axis. And a green means that, the algorithm has called it benign, and an orange means that the algorithm has called it pathogenic. Now, in an ideal scenario, there would be perfect match between ClinVar and these algorithms. In other words, the bottom panel would be all green and the top panel would be all orange. But as you can clearly see, that it's not so, and there is a lot more, disagreement among algorithms when it comes to benign. And some algorithms really are just not suited for example, the GenoCanyon here, it has a tendency to call everything pathogenic. So, and there are reasons for that. So you don't use this for functional predictions. And so you can see that there is much lower concordance for variants, which is missense variants, which are taking benign in ClinVar. But the pathogenic variants, it's a little better, and they are more concordant. Now, if you go to the next slide.
Hey, Raj.
Yeah.
Do you mind questions in between, or do you want to wait until the end?
No, sure. Go ahead.
This is Jonathan. I just had a quick question if you go back. So, I think what is sort of inherent in each of these algorithms is that they set some threshold that defines the difference between a, predicted deleterious or predicted benign. And that, that threshold basically tunes the algorithm to either be a little bit more aggressive about calling things pathogenic or damaging, whatever their term is, or, and so, there's certain of these algorithms that you really can't tune yourself, but there are some like CAD that you could set different thresholds if you wanted to. You could say, I want a CAD of greater than 20 or a CAD of, greater than 15 to distinguish, pathogenic versus benign. Did you play around with that any?
Yeah, so that's
the ones where you can actually adjust your thresholds? Yeah,
actually, I'll just briefly mention that, and actually that is an ideal way of doing things once you have chosen the algorithm. If you have enough benign and pathogenic, known benign and pathogenic variants for a given gene, you would have the tools, all the tools essentially, to calibrate the threshold for your algorithm and test new variants in that gene. And in this case, I mean, that could be essentially done for any gene and any algorithm, and you could get a threshold. But in the interest of time, I'm not showing. I am just showing how you would use one. If you just take the publicly available threshold, for example, DBNSFP has their own cutoff. They produce a threshold. And also the authors have suggested in some of these algorithms what threshold would you use, which gives, a good power to distinguish between pathogenic and benign variants. But you're right. Ideally, for a given gene, if you have a known set of from other evidence types, not in silico algorithm, benign and pathogenic variants, you could use that data set to find out what is the optimal threshold and the algorithm is performing best, and then you can use for newer variants in that gene.
Right, and ultimately the question you have to ask is, would you rather err on the side of overcalling things or undercalling things? And that the big issue.
And there are ways to do that. And I have done that, but I mean, if anyone is interested, I'm happy to show them offline how to do it. But it's definitely, you're right. But when you're looking at thousands of variants across, several genes, then it's not really practical. So that's the downside of it. Okay, oh, sorry. Jenny, if you go to the next slide, I just clicked something. So this is basically, brings out two caveats, and this is a table which gives you numbers. So of the figure, from the figure. So the caveat one is the concordance among in silico algorithms low for benign variants. Essentially, it means that in silico algorithms has a tendency to call variants pathogenic. And also false concordance can lead to erroneous inferences. This is not obvious from that figure, but what I mean is I'll show you in an example. So these are the numbers for the figure. So only 4%, so these is all the 18 algorithms. So only 4% of the variants, all the 18 algorithms were concordant, benign variants. And only 1% of the pathogenic variants, all the 18 algorithms were concordant. And this is ClinGen 1 star or above. And if you increase the confidence of the variant assertion, ClinGen 2 star or above, you could only, get 3.5% concordance for benign and 2% concordance. So it's not much. So, errors in ClinGen classification may not be, the main driver for this low level of concordance among large number of algorithms. And there is this false concordance which I just mentioned, which there are two variants, where all the 18 algorithms have said it's, pathogenic and but the I called it benign, and ClinGen has called it pathogenic. So, and there are several other of these examples. I'll show you only a few examples in the next slide. Jenny, can you go to the next slide? So this is an example of false concordance. So this is a benign variant. Benign in the sense that you can see it's in ClinGen. There are several assertions of benign or likely benign or uncertain significance, but mostly like benign or likely benign by several different laboratories. Now, if you go, Jenny, can you go to the next slide? Thank you. So if you go look into this variant in the variant curation interface, I mean, several of the algorithms, pretty much all 18 algorithms that I looked at call it damaging. And you can see that, in the interface, you can see for the same variant, several of the scores are damaging. Pretty much all of them are calling, in silico predictors are calling it damaging, whereas the variant is called as benign in ClinGen. So that is an example of a false concordance, and this can throw you off if you just use the in silico predictors as your main, one of your main criteria. So that this is a caveat that always has to be kept in mind, that the in silico predictors are not perfect. Sometimes they could give you opposite assertions than what you would predict based on other lines of evidence. So Jenny, can you go to the next slide? So, I mean, this is basically showing, in practice, no one uses these 18 algorithms. So people generally use a smaller number of combinations. And when you use smaller number of combinations, the concordance amongst them goes up, but so does the false concordance. That is basically they're asserting, they're concording, they're basically saying that this is damaging, but other pieces of evidence that's trying to say that this is, benign. So, and vice versa. So the fewer number of false concordance would increase the lower the number of algorithms that you use. And that is a caveat that one needs to keep in mind. So Jenny, if you go to the next slide. And the other thing is some algorithms are very sensitive to the alignment that is being provided. And I think the sequence variant interpretation of group of ClinGen will come up with a guideline how to incorporate proper sequence alignment or the minimal criteria for sequence alignment that that needs to be satisfied before making an inference. I mean, this is just to demonstrate P10. I mean, I use 3 different alignments and got the SIFT scores, which is sensitive to alignment. And you can see, and these red means a pathogenic variant, and green is a benign variant. And you can see for the same variant, which is along each column, there are widely fluctuating results depending on the alignment. So you need to have an alignment based on, you know, basically curated alignment for a given gene to get good results. Otherwise, you will get an erroneous assertion. So alignment is important, and there would be from the sequence variant interpretation group for ClinGen, there would be a recommendation, I think, eventually, that, you know, what is the proper alignment and what are the criteria that you need to look into before using some of these other tools which are sensitive to alignment. And this is a paper which outlines the problem and has a few algorithms which are sensitive, whose performance is sensitive to alignment. So if you go to the next slide. So the other thing is that there are different kinds of algorithms which is not really clear from the ACMG guidelines. So for example, there are certain algorithms which are not really algorithms. They are basically trying to say, such as this Philo-P, Sci-Fi, GAR, FirstCons, trying to say how conserved they are, or whether the region around them or that variant is constrained to a certain level. Whereas the other ones, they incorporate bunch of algorithms, or they try to making functional predictions about the algorithm. So in this figure is essentially taking all those scores from all these algorithms for all the approximately 15,000 variants and doing a clustering. And you can see that, you know, these algorithms cluster differently from the conservation matrix. So for example, this REVEL, meta-SJ, meta-LR, they are more like metapredictors and functional predictors. They're clustering differently. Their scores are clustering differently from the Philo-P and these, you know, conservation metrics. So in other words, if you took an algorithm and took their scores from this cluster, which is the Philo-P cluster, and combined them with REVEL, you are more likely to give you discordant results than if you had to take something from within the same cluster. So so the caveat here is combining conservation metrics with metapredictors or any other functional predictors are probably not the best idea, and you're more likely to result in the discordant assertion. So if you go to the next slide, Jenny.
But wouldn't the
oh, go ahead.
I'm sorry, it's Jonathan again. If you go back one slide, if you were only looking at, say, a couple of clustered algorithms, would that mean that they're likely making the same mistakes? So
true. Yeah.
Concordant, they might be concordant wrong,
yeah,
right? As opposed to looking at multiple disparate ones where when they agree, they're likely to be in agreement, right?
You're right. So in the couple of slides, so you need to know the performance of these algorithms, how they perform. All I can tell is, like, don't really, it's not best to mix conservation metrics with other functional predictors. I'll show you in the next couple of slides how well they perform, and you'll see that, well-performing algorithms, and you would definitely use among all the possible other algorithm combinations the ones that are performing very well. Yeah, you're right. And then that's in the next couple of slides. So Jenny, so this is basically what I've showed the caveats. Well, there's concordance amongst algorithms, and it would decrease if you increase the number of algorithms. But then you want to use a smaller set of algorithms. But if you use a smaller set of algorithms, there's an increased probability that variant prediction, that is the false concordances, will happen, and that they are sensitive to alignment, some of the algorithms. And in the last slide, the conservation matrix with functional predictors is more likely to give you discordant results. And also, these are the two which I didn't get into. And variants may be present in the training set of the algorithm used. So it's good to look for the variant whenever you choose an algorithm, whether it's present in the training set. I mean, if a pathogenic variant it's already present in the training set and it's being already labeled as pathogenic or benign, the algorithm will, always call it pathogenic or benign. So that would be not you don't want to test something which is present in the training set of the algorithm. So this would be probably true for most algorithms, where the ClinVar variants are like from earlier ClinVar variants, but the newer ones probably may not be already in the training set. But it's good to check if a training set is available. And the other thing is that Jonathan brought this up, that uncalibrated thresholds for pathogenicity may result in erroneous assertions. So you need, ideally, would need a way to calibrate it. So if you go to the next slide, Jenny. So as you mentioned, Jonathan, so there may be errors. Even if you choose from a cluster, they may be doing the same level of, they're error prone. So one needs to look at their performances. So which predictors perform consistently across diverse data sets. So what we did here is like on the x-axis is AUC, or A under the curve, which is performance. So when AUC of 1 means like very well performance, very good performance. I mean, AUC of 0.8 is generally considered a good performance in the machine learning field. And AUC of 0.5 or around that area, it means that essentially the algorithm is calling randomly pathogenic or benign variants that is have a very high error rate. So as you can see, I mean, each column is different kinds of data sets, which is basically ClinVar, 1-star variants, 2-star variants. These are the variants which are in dominant genes, and these are the variants which are in recessive genes. These are the variants which are in oncogenes, tumor suppressor genes. Then the genes are subdivided into high constant, low constant, and medium constant based on the missense Z-scores, and then their performance across those subsets of genes separately. And as you can see, the rank order doesn't really change, with REVEL performing the best in across all of them, as well as best 3. And these are in green, and you can see in green are the metapredictors, which is kind of not surprising. I mean, best 3 technically is also a metapredictor. It's an ensemble predictor. It uses a lot of features. So you can see that they are performing pretty well, and it's not surprising because these, at least REVEL, MetaSGN, they include some of these, or actually most of these algorithms, and combine them and then make a prediction. So it's not really that surprising, but if you had no data available, if you're just generally using the in silico algorithm, probably one of the top ones which are performing best will give you better results, and you have to make sure, of course, that the variant is not in that training set. So if you go to the next slide. So I mean, there are lots of caveats, as I've shown, and so there, I mean, this is part of this is essentially what I think, but this is a possible set of possible solutions or suggestions. So one is use gene-specific algorithms if available, because it includes the properties of the genes, but there are not many of them. I think there is one for CFTR, and there may be one at Stanford for MY87 as well. Alternatively, one could calibrate the algorithms to obtain thresholds on known variants in a gene. This is coming back to the point that Jonathan brought up. So essentially, you take a gene, take a known variants, a handful of pathogenic, a handful of benign variants, and then calibrate based on that an algorithm of your choice, and choose the highest performing ones. And then there is this, given that the conservation metrics do not really cluster at all with the other functional predictors, so probably best to ask if this is conserved, or and then separately ask if it's deleterious by prediction algorithms. So, and then it's best to use prediction algorithms after exhausting all sources of evidence. I'm saying this because there are caveats in it, and could, given, depending on the number of algorithms you're using, you may have false concordance rates. And also, given the caveats, it may not be best to elevate PP3 evidence to a strong or moderate category. And so if you go to the next slide. And then, I mean, the last thing I'll just briefly touch upon is the conservation, which is basically GARP, phylopy. Those are the evolutionary constraint measures, and FAST-cons is more of a conservation metric, which will give you a quantitative output. Now, these are sensitive to alignment, but I don't, so you probably need to test different kinds of alignments, which are possible for phylopy and FAST-cons, and I think also for GARP. But if you're getting it from DBNSFP, VP, then you have fixed choices. And for details of this, you could go to the help page and for the interpretation. And UCSC table browser, it allows you to generate all three and has a very good description of these, summary description of these. And lastly, I mean, one thing I would mention that you should want to manually check the alignment. And there are many ways to do this, and this is important for if you read the detailed text of the ACMG AMP guidelines. There is that, you know, if a variant, if a substitution is fixed in other primates, then it's most likely not pathogenic. That it explains there. So one quick way to use is to use homologene and check it. So in the next slide, I'll just show you how to do it if you guys are not already familiar with it. So you just go to NCBI, select homologene, and type in your gene name and limit it to human disease genes, which you can do it by the limits in the top. And then you could just click on under protein alignment, show multiple alignment. And if you click on that, and then if you go to the next slide, and you can see it's multiple alignments across primates, mice, and various other organisms. And you can see this is a variant which in DSP is valine 32 methionine substitution, but you can see the methionine is actually at that position in several primates, mouse and rat as well. So it's probably not likely to be a pathogenic variant, but this is a criteria that's mentioned in the ACMG guidelines, so this is a quick way to just check it. But there are many other ways to do this. So